April 26, 1986, 1:23 in the morning. Inside the control room of Reactor number 4 at the Chernobyl Nuclear Power Plant, a test that has been delayed for hours is finally approaching its conclusion. Outside, the nearby city of Pripyat is quiet. Tens of thousands of people live only a few kilometers from the plant. Most have no reason to believe that this night is different from any other. There has been no evacuation, no public warning, no visible emergency. But inside Reactor 4, the conditions are anything but normal. The reactor is operating at unusually low power. Its internal power distribution is unstable. Many of its control rods have been withdrawn. Large volumes of cooling water are moving through the core, and the reactor itself possesses characteristics that make this particular combination far more dangerous than the people in the control room fully understand. At exactly 1:23 and 4 seconds, the test begins. Steam to the turbine is cut. The turbine begins to slow. Its remaining rotational energy is now being measured. 30 seconds pass. The reactor remains intact. Then, at 1:23 and 40 seconds, the emergency shutdown system is activated. The control rods begin to descend. They are designed to stop the nuclear reaction. But during the first few seconds, something very different happens. Reactivity begins to increase. At 1:23 and 43 seconds, emergency signals register a rapidly accelerating rise in power. What happens next unfolds too quickly for any person in that room to stop it. To understand how one of the world's most powerful nuclear reactors reached this point, we have to go back. Not a week, not a month, just one day. The final 24 hours before Chernobyl. In April 1986, Chernobyl was part of the Ukrainian Soviet Socialist Republic inside the Soviet Union. The nuclear power plant stood roughly 100 kilometers north of Kyiv. But the city most closely connected to the plant was not Chernobyl itself. It was Pripyat. Founded in 1970, Pripyat had been created to house the workers of the nuclear complex and their families. It was young, planned, modern by Soviet standards. Apartment blocks rose above wide streets. There were schools, shops, sports facilities, and cultural buildings. Many of the people who lived there were young specialists, engineers, technicians, plant workers, their families. The city existed because of nuclear power, and nuclear power represented progress. Beside Pripyat stood 4 operating reactors. Reactor number 4 was the newest of them. It was an RBMK 1000, a massive Soviet-designed reactor capable of producing approximately 1,000 megawatts of electrical power. And to understand what happened during the final hours of April 25th, there are only a few things we need to understand about its design. The RBMK used graphite to moderate neutrons. It used water to cool the fuel. Water entered the reactor. Heat from nuclear fission turned some of that water into steam. The steam traveled to turbines. The turbines drove generators. Electricity was produced. In normal operation, an enormous number of physical processes and engineered systems worked together to keep the reaction stable. But the RBMK had an unusual and dangerous characteristic. Under certain operating conditions, when more of the cooling water turned into steam, the nuclear reaction could become stronger. This is connected to what engineers call the positive void coefficient. More steam could create more reactivity. More reactivity could create more power. More power could create more heat. More heat could create more steam. Under the wrong conditions, these effects could reinforce one another. That did not mean that every RBMK was constantly on the edge of exploding. It did mean that operating the reactor safely required a deep understanding of its behavior. And there was another problem. A problem hidden inside the very system designed to shut the reactor down. Reactor 4 was scheduled to be shut down for routine maintenance on April 25, 1986. The shutdown created an opportunity to repeat a technical experiment that had already been attempted before. On paper, the test had very little to do with nuclear physics. It was primarily an electrical problem. But because the equipment involved was connected to a nuclear reactor, The consequences of getting it wrong could be far greater than anyone expected. A nuclear power plant produces electricity, but strangely, it also depends on electricity to remain safe. Even after a reactor stops producing power for the electrical grid, cooling water must continue circulating through the core. Instrumentation needs electricity. Control systems need electricity. Safety systems need electricity. The reactor may have been shut down, but the heat does not disappear with the flip of a switch. Radioactive fuel continues producing what engineers call decay heat. Initially, that residual heat can still be enormous, so the cooling pumps cannot simply stop. Under normal conditions, the plant receives the electricity it needs from the electrical grid. If that external power is lost, emergency diesel generators are designed to start automatically. But in 1986, those generators needed time, not hours, not even minutes, but enough time to create a problem. Roughly 40 to 60 seconds could pass before the diesel generators were producing the power required by the most important systems. For a nuclear power plant, a minute can be a very long time. Engineers therefore wanted another source of electricity to bridge that gap, and the solution seemed obvious: the turbine. A turbine in a nuclear plant is enormous. Steam produced by the reactor spins its blades at high speed. The turbine is connected to a generator, and that generator produces electricity. When the flow of steam stops, the turbine does not immediately stop spinning. It slows gradually. Its enormous rotating mass continues moving because of inertia. Imagine turning off an electric fan. The electricity disappears immediately, but the blades continue spinning. Now imagine the same principle on an industrial scale. Could the remaining momentum of a massive turbine generator produce electricity for just a few more seconds? Enough to keep cooling pumps running until the diesel generators took over? That was the question. It was not a ridiculous idea. It was an engineering problem that needed an engineering answer. Similar tests had already been carried out at Chernobyl, but the results had not been satisfactory. The turbine voltage fell too quickly. Modifications were made to the electrical system. And now, before Reactor 4 entered its scheduled maintenance shutdown, engineers wanted to try again. The test procedure seemed straightforward. First, reduce reactor power. Then, stabilize the reactor at the required level. Prepare the pumps and electrical equipment. Disconnect steam from the turbine. Measure the turbine as it slowed. Observe whether it continued producing enough electricity. Then, shut the reactor down completely. If everything went according to plan, the experiment would last only a short time. Data would be collected. Reactor 4 would be shut down. Maintenance would begin. And life in Pripyat would continue as normal. There was no plan to push the reactor beyond its limits. No one entered the control room intending to create a disaster. No one believed they were beginning the final day of Reactor 4. But there was already a problem hidden in the relationship between the test procedure and the reactor on which it was going to be performed. The people responsible for the electrical experiment were interested in the turbine. They wanted to know how it behaved as it slowed down, but the reactor was not simply a passive source of steam. Its behavior changed depending on power level, coolant flow, control rod position, fuel conditions, and the concentration of radioactive products inside the core. At high power, the RBMK could behave very differently from the same reactor operating at low power, and the test would require precisely that, a reduction in power. There were also questions about the procedure itself. How closely had the test been coordinated with the reactor's nuclear safety requirements? Had everyone involved fully understood the interaction between the electrical experiment and the physical state of the core? Did the operators know all of the dangerous characteristics of the RBMK? Later investigations would show that the answer to that last question was especially important, because some of the reactor's most dangerous behaviors were not adequately communicated to the people operating it. The test was therefore not taking place in a perfect system where every person had access to perfect information. It was taking place inside a much larger organization, an organization with targets, schedules, procedures, hierarchy, technical assumptions, and a safety culture that would later come under intense criticism. Still, as April 25th began, none of this looked like the beginning of a catastrophe. It looked like maintenance, a test, another scheduled day at a nuclear power station. At 1:06 in the morning, Reactor 4 began reducing power. The countdown had started. April 25th, 1986. 1:06 in the morning. Power reduction begins. At this point, Reactor 4 is still operating at high power. There is no emergency, no major alarm, no obvious sign that anything is wrong. The reactor is being prepared for a planned shutdown. Operators begin lowering power gradually. This matters. Large nuclear reactors cannot always be treated like ordinary machines. You do not simply turn a dial from 100% to 0. Every change in power changes what is happening inside the core. Temperatures change. Coolant conditions change. The distribution of neutron activity changes. The concentrations of radioactive fission products change. A nuclear reactor is constantly evolving, and the way it behaved 10 minutes ago may influence the way it behaves now. At 3:47 in the morning, the reduction is temporarily stopped. Reactor thermal power is approximately 1,600 megawatts, roughly half of its nominal thermal output. The reactor remains at around this level for hours. Workers continue preparing equipment for the shutdown and the turbine test. From the outside, this is an ordinary industrial operation. Inside the control room, operators watch enormous panels filled with switches, lights, indicators, and gauges. This is long before modern graphical interfaces. There is no single screen displaying a perfect three-dimensional model of the core. There is no artificial intelligence warning the crew that a dangerous combination is slowly forming. Information is distributed across instruments. Some parameters must be calculated. Some values are not immediately available. And one of those values is particularly important: the operational reactivity margin, ORM. The term sounds complicated, but the basic concept is simple enough. The reactor's control rods contain neutron-absorbing material. By inserting or withdrawing these rods, operators can influence the nuclear reaction. Withdraw rods, and generally the reaction becomes stronger. Insert rods, and generally the reaction becomes weaker. The operational reactivity margin was a way of expressing the reactor's remaining control capability. Soviet operating rules required the ORM to remain above a certain minimum. The important number for our story is 15. 15 equivalent manual control rods. If the margin fell too far below that level, the reactor was not supposed to continue operating normally. And during April 25th, the margin did fall. Later calculations showed that at approximately 7:10 in the morning, the ORM was around 13.2 rods, below the required minimum. It would later recover. But this early moment is significant. It shows that even long before the explosion, Reactor 4 was already passing through conditions in which important safety limits required careful attention. Still, there was no explosion. The reactor remained stable. Power remained around 1,600 megawatts thermal. Morning became afternoon, and the plant continued preparing for the test. At approximately 1:05 in the afternoon, one of the turbine generators was disconnected. Preparations moved forward. The plan still seemed manageable. Reduce power, perform the electrical experiment, shut down Reactor 4. But then, at approximately 2 in the afternoon, the schedule changed. Not because of anything happening inside the reactor, but because hundreds of kilometers of electrical infrastructure outside the plant still needed the electricity Chernobyl was producing. 2 p.m. The test is approaching. As part of the planned procedure, the emergency core cooling system has been isolated. This system is designed to provide emergency water to the reactor if normal cooling is lost. Its isolation has often been presented in simplified retellings of Chernobyl as one of the reckless decisions that directly caused the explosion. The reality is more complicated. Later investigations concluded that disabling the emergency cooling system did not initiate the runaway nuclear reaction that destroyed Reactor 4. The accident would have happened in essentially the same way whether that system had been available or not. But the fact that a major safety system could remain unavailable while the reactor continued operating for many hours reveals something broader. The test was becoming more important than the original schedule. Procedures were being adapted to circumstances. And then, the electrical grid controller in Kiev made a request. Do not continue reducing power yet. The grid still needed electricity. Reactor 4 had to remain online. The test was delayed. The decision was not made because anyone at Chernobyl expected danger. From the perspective of the electrical grid, it made sense. The power was needed. So, Reactor 4 remained operating at approximately half power. The experiment would have to wait. An hour passes, then another, then another. The reactor continues producing electricity. The emergency cooling system remains unavailable. The test equipment remains prepared. The crew waits. Afternoon gradually becomes evening. And inside the reactor, something invisible is changing. Xenon 135. This is one of the most important characters in the story of Chernobyl. It cannot be seen, it cannot be heard. There is no tank labeled xenon that suddenly begins filling, but its concentration can dramatically affect a nuclear reactor. When uranium atoms split, they produce a range of radioactive fission products. Through radioactive decay, some of these products eventually produce xenon 135. Xenon 135 is exceptionally good at absorbing neutrons, and neutrons are what allow the nuclear chain reaction to continue. So, xenon behaves almost like a poison for the reaction. More xenon can mean fewer neutrons available to sustain fission. This is why operators sometimes talk about xenon poisoning. Now, imagine the reactor has been running at high power. A certain balance of radioactive products exists inside the core. Then, power is reduced. The neutron flux changes, but the radioactive materials already produced inside the fuel continue decaying. For a period of time, xenon concentration can increase. The result is a reactor that becomes increasingly difficult to control at low power. You attempt to increase the reaction, and the xenon absorbs neutrons. So, you withdraw more control rods. The xenon still suppresses the power. So more control authority may be removed from the core. This does not automatically produce a disaster. Nuclear operators understand xenon poisoning. It is a known physical phenomenon. But in the case of Reactor 4, xenon would later combine with other conditions: low power, withdrawn control rods, high coolant flow, a dangerous reactor design, and a test procedure that was now running many hours behind schedule. The delay also has a human consequence. The experiment had originally been expected earlier. Instead, it is pushed late into the night. Different operators are now involved. People who had prepared for one schedule find themselves working another. The night shift inherits a test it had not expected to conduct under these exact conditions. This does not mean the night crew was inexperienced or incapable. One of the myths surrounding Chernobyl is that the control room was filled with incompetent men who had no idea what they were doing. Later investigations rejected such a simple explanation. These were trained nuclear operators, but they were operating a machine with dangerous characteristics that were not completely reflected in the information, procedures, and training available to them. That distinction matters. A person can make a bad decision. A machine can have a dangerous design. An organization can have a poor safety culture, and all three things can contribute to the same accident. They do not cancel each other out. At around 3:20 in the afternoon, the operational reactivity margin is again comfortably above the minimum. On paper, there is still plenty of time to complete the test safely. Hours continue to pass. The sun goes down over Pripyat. Apartment windows begin lighting up. Children return home. Families eat dinner. Workers finish their shifts. To anyone living in the city, the nuclear plant on the horizon looks exactly as it did the day before. Nothing suggests that this night will be different. At the power station, Reactor 4 continues running. The test remains delayed. 9 hours after the interruption, permission finally arrives. At 11:10 p.m., the power reduction can continue. There are now just over 2 hours before the explosion. 11:10 p.m. Power reduction resumes. The reactor that has been waiting for hours is finally being taken toward the operating level required for the test. Inside the control room, the atmosphere is technical rather than dramatic. Numbers change. Operators make adjustments. Instructions are followed. Systems are prepared. At this stage, no one is running through corridors. No sirens are sounding. No one is shouting that the reactor is about to explode. This is what makes the final hours so unsettling. The disaster is approaching, but from the perspective of the people inside the control room, they are still solving operational problems. At midnight, April 25th becomes April 26th, a new day. At 12:05 a.m., Reactor 4 is at approximately 720 megawatts thermal. The original test plan had been associated with a higher power level, but power continues falling. A nuclear reactor at lower power is not simply the same machine producing less energy. Its physics changes. The distribution of neutrons can change. The effect of xenon becomes more important. The relationship between coolant and reactivity can become more unstable, especially in an RBMK. The operators need the reactor to reach a stable level. Then, something happens. At approximately 12:28 a.m., during a transition involving the automatic power control system, reactor power collapses. The neutron power falls dramatically, from hundreds of megawatts toward approximately 30 megawatts thermal. Almost nothing. Later accounts would disagree about exactly why this happened. Early Soviet explanations placed heavy emphasis on operator error. Later analysis made clear that the available evidence did not justify such a simple conclusion. But regardless of the exact cause, the reactor is now in a difficult condition. The power has fallen far below the planned operating level for the test, and the crew faces a choice. Stop. Shut the reactor down. Cancel the experiment. Try again another time. Or recover the power. They choose to recover it. This moment does not produce the explosion, but it is one of the most important turning points in the entire night. Because after the power collapse, xenon poisoning becomes increasingly significant. The reactor does not want to return to power. The invisible break inside the core is getting stronger. To overcome that break, operators begin withdrawing control rods. A little power returns, but not enough. More rods are withdrawn. The reaction begins to recover. 30 megawatts, 50, 100, slowly climbing. But the reactor does not return to the original planned test power. Eventually, the crew stabilizes it at approximately 200 megawatts thermal, far below the reactor's normal operating level, and far below the level at which the test had originally been expected to take place. The reactor is now running, but it has changed. Its neutron distribution has changed. Its xenon concentration has changed. Its control rod configuration has changed. The physical state of the core is different from what it was only an hour earlier, and one of the most dangerous mistakes we can make when reconstructing Chernobyl is to imagine that the reactor was either safe or unsafe, as though there was one exact second when it crossed a magical line. Reality is more complicated. Risk accumulated. One condition was added to another, then another. Low power, xenon poisoning, control rods withdrawn, a delayed test, systems configured for the experiment, unusual coolant conditions, a design with a strong positive void coefficient, and a control rod system with a dangerous characteristic that the operators did not fully understand. At 12:30 in the morning, none of these things has yet destroyed Reactor 4. The plant is still intact. The city is still asleep. There is still time to stop. But the margin for error is becoming smaller. Around 1 o'clock in the morning, Reactor 4 stabilizes at approximately 200 megawatts thermal. The crew continues preparing for the turbine rundown test. At approximately 1:03 a.m., another main circulation pump is switched on. Several minutes later, at approximately 1:07, an eighth pump is added. 8 main circulation pumps are now operating. Why does that matter? Because the pumps control how much water is moving through the reactor. Large amounts of relatively cool water are now passing through the core. At first, that sounds reassuring. More cooling should mean more safety. But inside an RBMK operating at very low power, the relationship between water, steam, and reactivity is not that simple. Water performs two important roles. It removes heat, but it also absorbs some neutrons. When water turns to steam, those steam bubbles contain much less liquid water. Neutron absorption falls. And because the RBMK's graphite continues moderating the neutrons, the nuclear reaction can increase. This is the positive void effect. Under normal operating conditions, other stabilizing effects can help control the reactor. But under these low power conditions, the positive void coefficient becomes extremely important. At the same time, the high flow of relatively cool water through the reactor suppresses steam formation. The core can appear stable, but it is a fragile stability. Think of balancing an object at the edge of a table. Nothing is moving, for the moment, but the amount of disturbance required to change the situation is much smaller than it appears. As the pumps operate, the test configuration is completed. Operators adjust systems to maintain water levels. Automatic controls struggle to compensate for the unusual conditions, and the reactor remains near 200 megawatts. There is another parameter the crew should be watching closely: ORM, the operational reactivity margin. But the system for calculating this value is not instantaneous. This is not a modern plant with every critical parameter constantly calculated and displayed in a clear warning interface. The Scala computer system processes information. Calculations take time. Operators cannot simply glance at one screen and instantly see an exact, real-time picture of the entire reactor core. Later investigators would reconstruct the reactor's state using recorded data, and those calculations reveal something deeply important. At approximately 1:22 and 30 seconds, the operational reactivity margin was around 8 equivalent manual control rods. The minimum was 15. 8. Nearly half of the required value. A reactor in this condition was supposed to be shut down, but the test continued. Why? There is no single answer. The importance of ORM itself had not been communicated as clearly as it should have been. Its connection to the dangerous behavior of the shutdown system was not adequately understood by the operating staff. The test had already been delayed for hours. The reactor had finally been stabilized. The equipment was configured. The experiment was ready. And on the control panels, Reactor 4 was still running. No explosion, no obvious runaway, no immediate visual sign that the situation had become catastrophic. At this point, the reactor is dangerous not because one thing has failed, but because almost every protective assumption is becoming weaker at the same time. Low power, 8 rods of margin, xenon, high coolant flow, an unstable power distribution, a large positive void coefficient, and a shutdown system whose first moments could produce the opposite of what its operators expected. The last of those problems is the most important, because in less than 2 minutes, someone is going to use that shutdown system. To understand the next 60 seconds, we need to look inside the RBMK control rods. In almost every description of a nuclear reactor, control rods are presented as something simple. They absorb neutrons, insert them into the core, and the nuclear chain reaction slows. Insert all of them quickly, and the reactor shuts down. This process is sometimes called a scram. In Chernobyl's Reactor 4, the emergency shutdown command was known as AZ5. Activate AZ5, and all control rods should move into the reactor. It sounds like the safest action anyone could take, and normally, it should be. But the RBMK control rods used at the time had a dangerous design characteristic. When many of the rods were fully withdrawn, their lower sections did not contain neutron-absorbing material all the way down. They included graphite displacement sections. Below these graphite sections were columns of water inside the channels. This geometry created a problem. Remember, in the RBMK, water absorbs some neutrons. Graphite helps moderate them. So when a fully withdrawn control rod began moving downward, The graphite displacement section entered the lower part of the reactor first. It pushed water out of that region. For a brief period, water that had been absorbing neutrons was replaced by graphite. Instead of immediately reducing the nuclear reaction, reactivity could initially increase. This became known as the positive scram effect, a shutdown command producing a temporary increase in reactivity. That sounds absurd, and in a well-designed safety system, it should be. But under ordinary operating conditions, the effect might remain relatively small. Reactor 4 is not in ordinary operating conditions. Many control rods are withdrawn. The operational reactivity margin is extremely low. The reactor is operating at a very low power level. Its internal power distribution is highly uneven. The positive void coefficient is strong, and because many rods are far from the core, activating AZ5 means a large number of graphite displacement sections begin entering the reactor almost simultaneously. The effect is especially dangerous in the lower region of the core. And there is another crucial issue. The control rods move slowly. From fully withdrawn to fully inserted takes many seconds. In a stable reactor, this can be sufficient, but a reactor entering a rapid positive feedback loop can change dramatically in only a few seconds. The system designed to stop Reactor 4 therefore has two serious weaknesses. First, it can initially increase reactivity. Second, it cannot insert the neutron-absorbing sections instantly. The operators in the control room do not fully understand the danger. They know AZ5 is the emergency shutdown. They expect it to shut down the reactor. They do not look at the button and think, this may destroy the core. That is why the final moments of Chernobyl are so important when we talk about safety. It is easy to blame a person for pressing the wrong button. It is much more disturbing when the person presses the correct button and the machine responds in an unexpected way. 1:22 a.m. The test is ready. The turbine is turning. The pumps are running. The reactor is holding near 200 megawatts. The city outside is sleeping. There is approximately 1 minute left. 1:23 and 4 seconds. The turbine rundown test begins. The steam supply to turbo generator number 8 is closed. Without fresh steam driving it, the turbine begins to slow. The enormous spinning machine still contains a huge amount of rotational energy. That energy continues turning the generator, and the electrical systems connected to it begin running from the turbine's remaining momentum. This is precisely what the engineers wanted to measure. How quickly will voltage fall? How long will the pumps continue operating? Can the turbine bridge the gap before emergency generators take over? The test that has been waiting all day is finally underway. For several seconds, nothing extraordinary appears to happen. The turbine slows. Pump behavior changes. Data is recorded. Inside Reactor 4, however, coolant flow begins changing. As the turbine generator slows, the power supplied to some circulation pumps begins falling. Water flow through the core decreases. Less water is moving through the fuel channels. The water already inside the channels absorbs heat. More of it begins turning to steam. More steam means more voids. More voids mean less liquid water absorbing neutrons. And in this reactor, that can mean more reactivity. The reactor begins to respond. The change is not immediately catastrophic, but the feedback is moving in the wrong direction. More reactivity, more power, more heat, more steam, more reactivity. The loop is beginning. 5 seconds pass. 10, 15. The turbine continues slowing. The control room instruments continue reporting values. 20 seconds, 25, 30. At this point, the reactor is still physically intact. There is no giant explosion building visibly in front of the operators. No one has been thrown from their chair. The test is still running. Then we reach one of the most debated moments in nuclear history. 1:23 and 40 seconds. 36 seconds after the beginning of the test, a Z5 is activated. Why? It sounds like a simple question. It isn't. Popular films, television dramas, and simplified retellings often show the operators desperately pressing AZ5 because the reactor is already obviously running out of control. It creates a perfect, dramatic moment. The men realize the danger. Someone reaches for the emergency button. Too late. But the historical evidence is less certain. Later investigators could not conclusively determine the exact reason AZ-5 was activated at that moment. It may have been a normal decision to shut the reactor down at the end of the test. That possibility changes the meaning of the moment completely. The person activating AZ-5 may not have believed he was fighting a disaster. He may have believed the experiment was essentially complete. Now shut down the reactor, exactly as planned. We should be careful here. We do not know the exact thought process inside the control room at 1:23:40, and pretending that we do would turn history into fiction. What we do know is what happened after the command. AZ-5 sends the signal. The control rods begin moving downward. Dozens of rods start entering the reactor core. At first, their graphite displacement sections enter the lower regions. Water is pushed out. Local reactivity increases, and Reactor 4 is in exactly the wrong state for this to happen. The power distribution is already unstable. The reactor contains regions where small changes can create large effects. The positive void coefficient amplifies steam formation. Control rods are far out of the core. The shutdown system now introduces a sudden positive pulse of reactivity into the lower portion. Power rises. Fast. Heat production increases. Water begins boiling more violently. Steam formation increases. That steam adds still more positive reactivity. Now the loop begins accelerating. Reactivity creates power. Power creates steam. Steam creates reactivity. The process feeds itself. 1:23:41. 1 second after AZ-5. The control rods are still moving. 1:23:42. The power is accelerating. 1:23:43. Only 3 seconds after the shutdown command, emergency signals register a rapid increase in reactor power. Instrument readings exceed 530 megawatts thermal. But this number does not describe what is really happening inside the core, because power is not increasing evenly. Some regions are becoming far more energetic than others, and the instruments were never designed to measure a reactor changing this quickly. The situation is becoming physically uncontrollable. The absorbing sections of the control rods are still trying to enter. They need time. The reactor is giving them seconds, and seconds are now too long. 1 hour, 23 minutes, 44 seconds. Power continues climbing. Exactly how high Reactor 4's output ultimately reached cannot be known with precision. Estimates vary dramatically. What matters is that it rose far beyond the reactor's normal operating limits, far too quickly. Fuel channels begin experiencing extreme temperatures and pressures. Inside the fuel assemblies, uranium dioxide fuel heats violently. Coolant flashes into steam. Pressure rises. The channels that carry water through the reactor begin to fail. 1:23:46. Circulation conditions change sharply. Pumps connected to the turbine rundown begin losing power. Flow decreases. More steam forms inside the channels. The positive feedback accelerates. 1:23:47. Recorded values change rapidly. Steam separator pressure rises. Water levels shift. Automatic systems respond. But the systems are reacting to a process already developing faster than their normal design assumptions. 1:23:48. More steam, more pressure, more power. The structure of the reactor itself is now under extraordinary stress. 1:23:49. An emergency signal appears indicating pressure increase in the reactor space. A fuel channel has ruptured. Once channels begin failing, the geometry of the core starts changing, and in a nuclear reactor, geometry matters. Fuel, water, graphite, control rods, all are arranged precisely because the position of materials determines how neutrons move. Damage changes that arrangement. More channels fail. High-pressure steam expands. The huge pressure tubes begin rupturing. The massive structure above the reactor is subjected to forces it was never designed to withstand. The control rods are still moving. Then their movement stops. They never reach the fully inserted position. At approximately 1:24 in the morning, operators record severe shocks. Explosions tear through Reactor 4. The exact physical sequence of the explosions has been debated for decades. The first major destructive event is generally associated with an enormous steam explosion. A second explosion follows. The upper structure of the reactor is violently displaced. Heavy components are thrown aside. The building is ripped open. Pieces of fuel, graphite, structural material, highly radioactive debris, all are ejected from the reactor. Some land on nearby roofs. Fires begin. The graphite moderator inside the destroyed core is exposed to air. The reactor that only seconds ago existed inside a controlled industrial structure is now open to the atmosphere. There is no massive containment building surrounding the destroyed core like those used in many Western reactor designs. Radioactive material can escape directly upward, and at that exact moment, a few kilometers away, Pripyat still looks like a normal city. The apartment blocks are still standing. Streetlights are still glowing. People are still asleep. Some residents hear the explosion. Some see flashes in the direction of the plant. Some go to windows or balconies. But almost no one understands what they are looking at. Hour zero has arrived. Immediately after the explosion, confusion dominates the plant. The scale of the destruction is difficult for people to accept. This reaction is important to understand. Human beings interpret events using what they believe is possible, and many people inside the Soviet nuclear system did not believe an RBMK reactor could explode in the way Reactor 4 had just exploded. So when instruments failed, when radiation readings behaved strangely, when pieces of graphite appeared outside the building, the mind searched for explanations that still fit the old model. Perhaps a tank had exploded. Perhaps part of the cooling system had failed. Perhaps the reactor was still intact. Some operators initially continued behaving as if the core itself might still exist inside the reactor vessel. But it did not. The reactor was open, and pieces of its core were scattered around the site. Firefighters were called. To them, the emergency initially looked like an industrial fire. Buildings were burning. Roof sections were on fire. There were flames. So they did what firefighters do. They approached the plant. Many had no idea that the dark material lying around parts of the site was graphite from the reactor core. No idea that radiation levels in some locations were extraordinarily high. Some of the radiation instruments available at the plant could not even measure the true levels. They reached their maximum readings. And when an instrument displays its maximum value, there are two possibilities. The radiation level is exactly at the maximum, or it is far above it. In the first minutes of Chernobyl, that distinction was deadly. Workers and firefighters moved through areas with invisible radiation intense enough to cause severe damage in very little time. There was no smell, no color, no physical barrier warning them to stay away. Some would begin feeling symptoms within hours, but for now their priority was obvious. Stop the fires from spreading, protect the other reactor units, keep the disaster from becoming even larger. And remarkably, they succeeded in preventing many of the surrounding fires from producing additional catastrophic damage. Meanwhile, Pripyat was not evacuated. The city remained occupied through the night. Morning would arrive. People would wake up. Children would go outside. Families would look toward the damaged plant. Some residents would notice unusual activity. Military vehicles, police, officials. A strange metallic taste would later be recalled by some witnesses, but there would still be no immediate mass evacuation. The explosion occurred shortly after 1:23 in the morning. Pripyat would not begin evacuating until the afternoon of the following day. For roughly 36 hours after the accident, tens of thousands of people remained only a few kilometers from a destroyed nuclear reactor. But that is another countdown. Our story is about the hours leading to hour zero, and what those final hours reveal about why Chernobyl happened. In the years immediately following the accident, the official explanation was comparatively simple. The operators were blamed. They had violated procedures. They had operated the reactor improperly. They had disabled safety systems. They had allowed the operational reactivity margin to fall below limits, and they had continued a dangerous test. Some of those statements contained truth. The crew did make decisions that contributed to the accident. Important limits were violated. The test should have been abandoned under several of the conditions that developed that night. The reactor should not have continued operating with such a low reactivity margin. But as investigations continued, the explanation changed. Because blaming the control room alone could not explain why pressing the emergency shutdown button caused the reactor to become more reactive. It could not explain why a reactor could develop such a large positive void coefficient. It could not explain why operators were not clearly informed about the dangerous positive scram effect. It could not explain why previous warning signs involving RBMK reactors had not produced more effective design changes. Later investigations gave much greater weight to the reactor design, the control rods, the positive void coefficient, the slow emergency shutdown, the information supplied to operators, the design of the safety systems, and the safety culture of the Soviet nuclear industry itself. Chernobyl, therefore, becomes much more difficult to reduce to heroes and villains. This was not one reckless man destroying a perfect machine, and it was not one defective machine destroying a perfect crew. It was a system failure. Human decisions interacted with engineering flaws. Engineering flaws interacted with poor information. Poor information interacted with organizational culture. Organizational culture influenced the way procedures were written and followed. And all of it met inside Reactor 4 during one extremely unusual operating condition. This is why Chernobyl remains important far beyond nuclear energy. Major disasters often look simple after they happen. We know the ending, so every earlier decision seems obvious. Why didn't they stop? Why didn't they know? Why didn't someone see what was happening? But the people making decisions before a disaster do not have the advantage we have. They cannot see the documentary. They cannot read the investigation report. They do not know which ordinary-looking problem will become historically important. At 2 p.m. on April 25th, Reactor 4 was still operating. At 11:10 p.m., there was still no disaster. At midnight, there was still no disaster. At 12:28, after the power collapse, there was still an opportunity to stop. At 1 a.m., Reactor 4 was still intact. At 1:22, the city outside still had no reason to believe anything extraordinary was happening. At 1:23 and 4 seconds, the test began. 36 seconds later, AZ-5 was activated. 3 seconds after that, the reactor was entering an uncontrollable power excursion. And less than a minute after the test began, Reactor 4 was destroyed. 24 hours earlier, the day had looked ordinary. Workers followed schedules. The grid requested electricity. Operators adjusted power. Engineers prepared a test. Families lived their lives. Nothing announced itself as the beginning of Chernobyl, and perhaps that is the most uncomfortable lesson. Catastrophes rarely begin with a moment that looks like catastrophe. They begin with small decisions, delayed actions, accepted deviations, assumptions, design compromises, warnings that do not appear urgent enough, problems that seem manageable, until the system has moved so far from normal that one final action is enough to expose everything that was already wrong. At Chernobyl, that final action may have been the very command designed to make the reactor safe. AZ-5, the emergency shutdown, 1:23:40 a.m. The button is pressed, and within seconds, history changes. Because history rarely begins at hour zero. It begins before, sometimes years before, sometimes hours before, and sometimes in the final 24 hours.